we're going to talk a little more about energy conservation. So earlier we sort of talked about this idea that there's a local statement here that tells you about how the electromagnetic energy increases or decreases in some location, right? So this is the so-called energy density, and that's done by a transport of the energy across some sort of boundary through this Poynting vector, which is defined here. Now, the idea behind this is really we want to track all of the energy and what happens um, more broadly in the sense of an electromagnetic system, so more globally. And so, in fact, a more careful statement of this is actually that the total energy in any sort of situation where we are considering sort of the mechanical energy and the electromagnetic energy is related to this transport of energy density across a boundary. So here, while this might be stored in the fields, um, this is actually the particle energy. So this is like kinetic energy associated with particles that are in the system. It could be some sort of thermal energy, other forms of potential energy, and so forth. But the idea is that the particle plus field energy gets transported by the so-called Poynting vector, right? This is the thing that sort of is the energy density current, and it moves things around. And so when we actually want to understand more globally what is going on, so if we want to make a global statement of this, we can actually integrate this stuff over a volume. So if we look at the time derivative of a volume integral of the energy density um, associated with the mechanical and the electromagnetic, we then are actually integrating over a volume the Poynting vector. And so through the divergence theorem, what we have is a closed integral over some area of the Poynting vector. And so I think it's worth sort of taking a moment to state that, mainly that the time rate of change of the integral of the energy density associated with the mechanical and the electromagnetic energy, namely the time rate of change of the total mechanical energy plus the total electromagnetic energy, is exactly equal to the rate of transport of that energy across any boundary. So if you're looking at a sort of a volume that has a total amount of mechanical and electromagnetic energy, the way that that gets transported across the boundary has to do with what S looks like at every point in space uh, over the area that you are transporting the stuff across the boundary. So really what this is this global statement of energy conservation, namely that the rate of increase of all of the energy in a given volume is equal to the sort of negative outflow of that energy. And the outflow is a result of the Poynting vector carrying the energy away, and this is both the electromagnetic and the mechanical energy. So what's really kind of interesting about this is that, we can have situations where there is no outflow of energy, right? So that is that where, the S vector vanishes everywhere. And so we have just simple energy conservation. But we can also have situations where the mechanical energy is zero or it doesn't change. And so the Poynting vector, the way that it transports energy, can work to sort of just change the field situation. What is the energy associated with the fields? So in the last video, what we're going to do is just do a quick example of how this works and how it's related to a really simple situation of a steady current.